Hi everyone, welcome to my YouTube channel. Today, I will be talking about control charts, including Xbar chart, Rchart, and Rchart. Let's get started. As we know, many quality characteristics like a specific dimension on the part, like length of these camshaft, or the length and diameter of these screw, or the amount of the resistance in the resistor, can be expressed in terms of the numerical measurement. These are quality characteristics which need to be checked. So, single measurable quality characteristic such as dimension, weight, or volume is called a variable. When dealing with a quality characteristic as a variable, it is usually necessary to monitor both the mean value of the quality characteristic and its variability. Control of the process average or mean is usually done with the Xbar control chart. Process variability can be monitored with either a control chart for the standard deviation called the S control chart or a control chart for a range called R control chart. The R control chart is more widely used. It is important to maintain control over both the process mean and process variability. For example, in this figure, both the mean and standard deviation are in control at their nominal values. Most of the process output falls within the specification limits. In this figure, the mean has shifted from μ0 to μ1, resulting in a higher fraction of non-conforming products and higher failure rates. And in this figure, the process standard deviation has shifted from σ0 to σ1. This results in higher process fallout, even though the process mean is still at the nominal value. So, you see that how process mean shift and variability could lead into higher failure rate. The purpose of the control chart is to control these process variables. Suppose that m samples are available. In this example, 25 samples. And each sample contains n observations on the quality characteristic. In this example, 5 observations for each sample. 1, 2, 3, 4, and 5. Typically, n, the number of observations, is a small number, often 4, 5, or 6. Let x1 bar, x2 bar, x3 bar till xm bar be the average of each sample. For example, x1 bar is the average of these 5 observations. x2 bar is the average of these 5 observations, and so on. The best estimator of process average is grand average, or x double bar. This will be used as a center line on the control chart. For example, the x double bar for this case would be the average of these values divided by 25 samples. To construct the control limit, we need an estimate of standard deviation S. How we can get that? We will use the range method to have an estimate of standard deviation. The range of each sample is defined as the maximum observation minus minimum observation for each sample. Let's call it R1, R2 till R25. The average range is the average of all these ranges. Let's call it R bar. This is used as center line in Rchart. Suppose these 25 samples are taken from the manufacturing process when we think the process is in control. The interval of time between the samples or subgroups is 1 hour. For example, the interval between the first sample and the second sample is 1 hour. In that 1 hour, you have time to measure the sample, which include 5 observations. Here are control charts for the data that we have already collected. The first one is Rchart, and the second one is Xbar chart. To analyze these charts, it's better to begin with Rchart, because the control limits on the Xbar chart depend on the process variability. And we know that the process variability can be captured from Rchart. Here are formulas for constructing the control limits on the Rchart and Xbar chart. UCL is upper control limit and LCL is lower control limit. A2, D3, and D4 in these formulas are found from control chart table, tabulated based on the observations in the sample. For example, for 5 observations in sample, A2 is 0.577, D3 is 0, and D4 is 2.114. Okay, if all points in these plots inside the control limits and there is no systematic behavior in the plot, we can conclude that the process was in control in the past and the trial control limits are suitable for controlling current or future production. Okay, if all points in these plots inside the control limits and there is no systematic behavior in the plot, we can conclude that the process was in control in the past and the trial control limits are suitable for controlling current or future production. As we mentioned, to analyze these charts, always begin with Rchart, because the control limits on the Xbar chart depend on the process variability. It's obvious from these formulas as well. You need R bar here in these equations. From these equations, we found that the center line for Rchart is 0.3252. Then 25 sample ranges, R1, R2, R3 till R25 are plotted on the Rchart in this figure. There is no indication of out of control condition. So Rchart indicates that process variability is in control. We are okay to construct the Xbar chart and put control limits on it. From this chart, we can conclude that the process is in control. This means that the process is consistent and predictable. So the question here is, what does it mean for a range chart to be in statistical control? Okay, this means that variation within the subgroup is consistent from subgroup to subgroup. Okay? For this example, it means that the range between the largest and smallest dimension is the same for all parts. There is no statistical difference between these ranges. The average range will be 0.3252 microns, but it can vary anywhere from 0 to 0.68 microns. Since the range chart is in control, you can estimate the standard deviation. In this equation, the value of D2 for 5 observations in sample is found in this table, which is 2.326. So the estimated standard deviation is 0.139 for this process. Let's look at another example of control chart with subgroup. Suppose you are a quality engineer at automotive parts factory and you monitor the length of camshafts. 3 CNC machines manufacture camshaft for 3 shifts each day. So machine 1, machine 2, and machine 3. You measure 5 camshafts for each machine during each shift. For example, at first shift, you select 5 parts from the machine 1 and measure the lengths and record them here. You take 5 parts from machine 2, measure them and record them here. And finally, pick 5 parts from the third machine and measure them and record them here. Repeat this process for 19 more, in total 20 shifts. The question is how to monitor the camshaft lengths for each machine or for all machines together. Here we would like to use Xbar Rchart for each machine to monitor the camshaft lengths. These charts are a very powerful tool for monitoring variation in a process and detecting changes in either the average or the amount of variation in the process. So the Xbar Rchart is a type of control chart that can be used with variables like this. Xbar Rchart is a method of looking at 2 different sources of variations. One source is the variation in subgroup averages. The other source is variation within a subgroup. So, we should create an Xbar Rchart for each machine to monitor the camshaft length. Use these charts to monitor the mean and variation of the process. We can also use this control chart to monitor process stability over time so that you can identify and correct instabilities in a process. To use Xbar Rchart, the data should be continuous and should be in time order because control charts detect changes over time. The data should be collected at appropriate time intervals. We should collect data at equally spaced time intervals. For example, every hour, every shift, or every day. And finally, the subgroup size should be 8 or fewer observations. For subgroups that have 9 or more observations, it's better to use Xbar Schart. In Minitab, choose Stat, then Control Charts, and then Variable Chart for subgroups, and then select Xbar R. From drop-down menu, select All Observation for a chart are in one column. And then enter Machine 1, Machine 2, and Machine 3. Go to Xbar R options and select Test 1, 2, and Test 7. Test 1 says if 1 point more than 3 standard deviation, then identify the point. Test 2 says that if 9 points in a row on the side of the center line, then identify it. Test 7 says that if 15 points in a row within 1 standard deviation of center line, then identify those points. Minitab will create 3 Xbar R charts, 1 chart for each machine. The engineer looks at the R chart first because if the R chart shows that the process variation is not in control, then the control limits on the Xbar chart are inaccurate. The R charts for all 3 machines shows that the process variation is in control. No points are out of control, and all the points fall within the control limits in a random pattern. The points vary randomly around the center line and are within the control limits for both charts. No trends or patterns are present. By default, Minitab conducts only test 1, which detects points that fall outside of the control limits. However, if you conduct additional tests, then points can fail multiple tests. The output shows exactly which points failed each test. The Xbar chart shows that machine 2 is in control, but machine 1 and 3 are not. On the Xbar chart for machine 2, no points are out of control, but machine 1 has one out of control point, and machine 3 has 2 out of control points. So you need to investigate the cause of out of control points. Please note that for subgroups that have 9 or more observations, use Xbar Rchart. If you don't have subgroups, use IMR charts. If your data are counts of defectives or defects, use an attribute control chart, such as P chart or U chart. You can plot Xbar chart or R chart separately. To do this, go to the Stat, Control Charts, then Variable Charts for subgroups, and then select R. Then select Machine 1 and Subgroup ID and hit OK. And the same thing for the Xbar chart. Here are the results. We previously noted that a control chart can indicate an out-of-control condition even though no single point outside the control limits, if the pattern of the plotted points, like all of these charts, exhibit non-random or systematic behavior. In many cases, the pattern of the plotted points will provide useful diagnostic information on the process, and we can use this information to make process modifications that reduce the variability. In interpreting on the chart, we must first determine whether or not the R chart is in control. Never try to interpret the Xbar chart when the R chart indicates an out-of-control condition. In the normal pattern, the random variables Xbar and R are statistically independent and randomly distributed around the center line. So Xbar and R should behave independently on the control chart. No correlation between the Xbar and R values. The second pattern is an increasing or decreasing trend, or continuous movement in one direction. These trends are usually due to a gradual wearing out of a tool or some other critical process component. The next pattern is cyclic pattern. Such a pattern on the Xbar chart may result from systematic environmental changes such as temperature, regular rotation of operators or machines, or fluctuation in voltage or pressure or some other variables in the production equipment. The next pattern is systematic pattern. Test 4 in Minitab detects systematic variation. You want the pattern of variation in the process to be random, but a point that fails test 4 might indicate that the pattern of variation is predictable. A mixture pattern happens when the plotted points tends to fall near or a little outside of the control limits, with relatively few points near the center line. A mixture pattern is generated by 2 or more overlapping distributions, generating the process output. Upward or downward shift in process level is another pattern, which may result from the introduction of new operators, or changes in method, raw materials, or machines, a change in the inspection methods or standard, or change in either the skill, attentiveness, or motivation of the operators. The last pattern is stratification, or tendency for the points to cluster around the center line. One potential cause of stratification is incorrect calculation of control limits. This pattern may also result when the sampling process collects one or more units from the several different distributions within each subgroup. In this case, R incorrectly measures the variability between the different underlying distributions. In Minitab, use tests for spatial causes to determine which observation you may need to investigate and to identify specific patterns in your data. We are going to release video series on different topics including application of statistics in manufacturing and quality control, robotics and mechatronics, industrial machine vision, system dynamics, finite element analysis with abacus, GD&T and tolerance analysis, and many other interesting topics. Don't forget to subscribe to this YouTube channel to get notified when a new video on this topic is released.